नहीं हूँ, जान ही रहा।
सोच रहे हैं। So first of all, I would like to thank you, Dr. R.K. Singh, for giving me the opportunity, and Ahmedabad University for organizing this conference. So basically, PVA polymer. Before going into the detail into my work, first of all, I would like to give an introduction, experimental work, results and discussion. Then I will show some application, and then I will discuss about some facility. So first of all, polyvinyl alcohol. We know polyvinyl alcohol is a water-soluble polymer, and it has a very good attractive property: water solubility, film forming ability, and biodegradability. And it has a lots of wide range of application in the textile industry, adhesive, sealant, and paper industry. So basically, the problem with most of the PVA-based polymer is that people use to process this PVA polymer for solution processing only. So they did not go into the melt processing. The reason behind this is that due to the strong intramolecular attraction in the PVA molecule, the processing window of the PVA polymer is very less. So let's say the PVA polymer onset of melting is around 230 degrees Celsius, and the melting temperature, degradation temperature is around 278 degrees Celsius. So it is very difficult to melt process the PVA polymer. So as we know, the melt processing has lots of wide application. So my objective initially was to enhance the processing window so we can melt process the PVA polymer. So for that, I have synthesized the lithium salt of alific acid, and I mixed with the PVA polymer using a solution processing. I prepare the PVA composite film. So next, when I check the properties, then you can easily show that the roughness of the PVA composite polymer compared to the neat PVA polymer is increased. So later I will discuss why this roughness is important for the nanogenerator application. Again, the roughness is also shown in the 3D image of AFM. You can observe that the roughness is very high compared to the neat PVA polymer. Further characterization into the X-ray analysis and FTR analysis, we have observed that how the bonding between the hydrogen bonding enhanced. The extent of hydrogen bonding is find out from the amorphous peak of 1096 and the crystalline peak of 1143. We divide the ratio of the absorption intensity, and we observe that the extent of hydrogen bonding is increased. So what is happening here? Actually, the incorporation of the LIS salt into the PVA matrix results into the more intermolecular hydrogen bonding and breakdown in the intramolecular hydrogen bonding in between the PVA crystallite. So the crystallinity. So here you can see the interaction. So ultimately, the interaction of the LIS salt and PVA molecule, that is the crystallite region. So that is the intramolecular hydrogen bonding, and we result in the intermolecular hydrogen bonding. This bond is much weaker, which results into more amorphous in the composite film. So due to this extent of interaction of the formation of the intermolecular hydrogen bonding, we have seen a very good results in the thermal properties. So you can clearly see that the melting temperature for the pure PVA is around 230 degrees Celsius, and at a different weight percent, when it comes at a 15 weight percent of LIS salt, we observe that the melting temperature is quite reduced to 198 degrees Celsius. And we also observe that the crystallinity is decreases from around 42 to 26. So ultimately what we observe that the degradation temperature is also For pure PV, it was around 278, and finally we got around 355 degrees Celsius. So ultimately, we are getting a wide processing window. So wide processing window, this will help in the well processing of the PVA polymer in a bulk scale, I mean in a large scale. So finally, we have also characterized to observe the TZ. We have observed the decrease in the TZ. So further, we have done the dielectric characterization. So here we have observed that there is an interfacial polarization happening when there is a decrease. When we observe that the decrease in the frequency, we observe a high dielectric constant value. It is due to that the molecule get a very less time to polarize, so resulting in the very high dielectric constant value. So the dielectric constant value for the 15 watt% is very high compared to the pure PVA. So I will discuss why this dielectric constant value is important for the nanogenerator application in the later. So as we know, in a wearable electronics, when we discuss about the flexibility is very, very important. Although the PVA is flexible, but what we observe that further incorporation of the LIS salt into the PVA matrix, there is a decrease in the flexibility. Increase in the flexibility. So we observe that you can observe the displacement for the neat PVA is around 300 nanometer, but with the incorporation of the PVA LIS salt, the displacement increases. That means you are applying the same force and you are getting a more displacement. That means your sample is more flexible compared to the neat PVA polymer. So coming into the device application, so I fabricate the device. So here we use the copper electrode and the Kapton film and PVA composite film and the device structure. So these are the two different dielectric material I have used. So what happened, due to this contact force, there is a transfer of these charges due to the different work function, resulting in a output voltage. So here we observe that this is the forward connection and this is the reverse bias voltage, and we obtain the different output and we get a very good output at a 15 watt% sample, and this is the zoom view of the pressing and releasing. That means what happening, my device is like this. So when I tap, there are different modes of triboelectric nanogenerator, but I am using the vertical contact separation mode. So when you tap the device, it results into the output voltage. So this is the press and release. So when you tap, you get the output voltage, and when you release, you get another release output. So this is the charge density I have calculated and the short circuit current. Going into more into depth of to determine the power and DC voltage, here I have done the various output voltage across a different resistance. So finally obtain that current at a different resistance, voltage at a different resistance. As we know, P equal to V square by R. So from that I calculate the power curve, and this is the DC voltage. So we convert it using that circuit that you can observe. So finally what we did, we try to glow LED bulb using our device. So finally this is the IITB logo that I tried to glow, and we characterize the charging characteristic of my device. So you can observe that within just 50 seconds of the tapping the device, you can easily generate around 6 volt. So which is enough to charge a mobile device. And this is under finger tapping, and this is that is under foot pressing. So here I have tried to charge different capacitor. So when we increase the capacitor, there is a decrease in the voltage. As we know, Q equal to CV. So when you go into a higher capacitor, to charging a higher capacitor, we get a lower voltage at a more interval of time. So finally what I did, I tried to use my different human motion, to check how many voltage we can obtain by the device. So I tried foot tapping, finger tapping, gently touch the device, jogging also, walking, knee bending. So these are the various different output voltage of my device. Finally, not only this, ambient and motion, human motion I have tried. I have also tried with a pen to check how the changing of the device. So I obtained that my device is showing a different characteristic for a different letter. So it is giving a different signal. So this can be a future, I mean, a future security application can be used for a security application. However, there it is not 100% accuracy. It is around 80% accuracy of getting the exact stroke of the pen, of your pen. So finally, I tried to use this device in sports. So what I did, I take a tennis ball. So I tried to put in a different angle, let's say 90-degree angle, 60-degree angle, and 30-degree angle. So I tried to put the ball on my device, and I observed the output voltage. Here you can see the schematic. So I obtained that at a 90-degree dropping of the ball, the voltage is high compared to 30 and 60 degree. The result is that when you drop the ball from a 90-degree, so there is a high contact of the surfaces, resulting in a more output voltage. So finally, I have tried to the boundary detection of the in a tennis sports. So we know that most of the tennis sports sensing application we use normally current days is camera. People use camera. So normally in indoor application, it is not easy for us to detect using a camera. Suppose we are playing a tennis, and I just didn't observe that the ball touches my boundary or not, right? So what I checked is that suppose if I make the device, if I put the device in the boundary line, if the ball touches, then it will show the ball is strike. So I just immediately get to know that okay, the ball strike my boundary. However, if ball doesn't strike the boundary, you can clearly observe that the ball doesn't strike. So further, I designed an IoT system. So using a Arduino and voltage divider circuit, because my voltage is more than 5 volts, so I have to decrease the voltage using a voltage divider circuit so that the Arduino doesn't get damaged. And further, I use the Bluetooth module and programming. I can clearly observe in a monitor that ball is strike. So now it has become easy that you are playing a tennis and you get to know easily that whether the ball strike the boundary or not using some kind of display on the display panel. So finally these are my highlights. So what I have done that I prepared the composite film with a high processing window. Also, I have seen that this device, I prepared the device that gives very high voltage output and can be used as an application of biomotion energy harvesting and application as a tennis sports. Finally, I would like to acknowledge my professor Arup Ranjan Bhattacharya and Abhijit Sangle for the facility and safe IIT Bombay. So here, as all of you are here, so I would like to introduce to one of the facility in IIT Bombay that I handle. That is the broadband dielectric spectroscopy. So here we can do a various frequency range and temperature dependent dielectric measurements. So with this, I would like to thank you. Thank you so much.
Thank you. Thank you very much, Mr. Prasenjit Dey.